The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today I'm going to tell you about flux of a vector field through a curve. So, in case you've seen flux in physics, probably you've seen flux in space, and we're going to come to that in a couple of weeks. But for now, we're still doing everything in the plane. So, bear with me if you've seen a more complicated version of flux. We're going to do the easy one first. So, what is flux? Well, flux, it's actually another kind of line integral. So let's say that I have a plane curve and a vector field in the plane. Then the flux of F across the curve C is, by definition, it's a line integral that I will use notation f dot n ds. So I have to explain to you what it means. But let me first box that, because that's the important formula to remember. That's the definition. So what does that mean? So first, I have to tell you what is this little n. So n, the notation suggests, it's a normal vector. So what does that mean? So I have a curve in the plane, and I have a vector field let's see, the vector field will be yellow today. And I will want to integrate along the curve the dot product of f with the normal vector to the curve, the unit normal vector to the curve. So that means a vector that's at every point of the curve perpendicular to the curve and of length 1. So n everywhere will be the unit normal vector to the curve C, pointing 90 degrees clockwise from T. So what does that mean? That means, I have two normal vectors, one that's pointing this way, one that's pointing that way. I have to choose a convention. And the convention is that the normal vector that I take goes to the right of the curve as I'm traveling along the curve. So imagine that you're walking along this curve, then you look to your right, that's that direction. Okay? So what we will do is we'll just, at every point along the curve, we'll do the dot product between the vector field and the normal vector, and we'll sum that along the various pieces of the curve. So what this notation means is that if we actually break C into small pieces of length delta S, then the flux will be the limit, as the pieces become smaller and smaller, of the sum of f dot n delta S, where so I take each small piece of my curve, I do the dot product between f and n, and I multiply by the length of a piece, and then I add these together. That's what the line integral means. Of course, that's, again, not how I will compute it. So just to compare this with work, see, conceptually, it's similar to the line integral we did for work, except, well, the line integral for work So, sorry, work is the line integral of f dot dr, which is also the line integral of f dot t ds. That's how we reformulated it. That means, we take our curve and we figure out at each point how big the tangent component. I guess I should probably take the same vector field as before. So let's see. My field was pointing more like that way. So what I do at any point is I project f to the tangent direction, and I figure out how much f is going along my curve. And then I sum these things together. So, I'm actually summing. Oh, that's the right color. The tangential component of my field f. Okay, so roughly speaking, the work measures, when I move along my curve, how much I'm going with or against f. Flux, on the other hand, measures when I go along the curve, roughly how much the field is going across the curve, counting positively what goes to the right, negatively what goes to the left. Okay, so flux is integral of f dot n ds, and that one corresponds to summing the normal component of the vector field. Okay, but apart from that, conceptually, it's the same kind of thing. Just the physical interpretations will be very different. But for a mathematician, these are two line integrals that you set up, compute pretty much in the same way. Okay. So let's see. I should probably tell you what it means. Why do we make this definition? What does it correspond to? So the interpretation for work made a lot of sense when f was representing a force. Then the line integral was actually the work done by the force. The interpretation for flux makes more sense if you think of f as a velocity field. Okay, so what's the interpretation? Let's say that f, so for f, a velocity field. So that means, I'm thinking of some fluid that's moving, maybe water or something, and it's moving at a certain speed, and my vector field represents how things are moving at every point of the plane. So I claim that flux measures how much fluid passes through the curve C per unit time. So if you imagine that, maybe you have a river and you're somehow building a dam here, but, a dam with holes in it so that the water still passes through, then this measures how much water passes through your membrane per unit time. Okay, let's try to figure out why this is true. Why does this make sense? So let's look at what happens on a small portion of our curve C. So I'm zooming in on my curve C. Sorry, I guess I need to zoom further. Okay. So, that's a little piece of my curve of length delta S. And there's a fluid flow. So on my picture, things are flowing to the right. So here I'm drawing a constant vector field because, if you zoom in enough, then your vectors will pretty much be the same everywhere. Right? If you, enlarge the picture enough, then things will be pretty much a uniform flow. So now, how much stuff goes through this little piece of curve per unit time? Well, what happens over time? The fluid is moving while my curve is staying in the same place. So it corresponds to something like this. Okay? So I claim that what goes through C in unit time is actually going to be a parallelogram. Okay, so here's a better picture. I claim that what will be going through C is this shaded parallelogram to the left of C. Well, let's see if I move for unit time. Okay, it works. Okay, so that's the stuff that goes through my curve in a unit time for a small portion of curve. And of course, I would need to add all of these together to get the entire curve. So let's try to understand how big is this parallelogram. So, to know how big this parallelogram is, I would like to use base times height or something like that. And maybe I want to actually flip my picture so that the base and the height make more sense to me. So let me actually turn it to this. Okay, and in case you have trouble reading the rotated picture, let me redo it on the board. So what passes through a portion of C in unit time is the contents of a parallelogram whose base is on C, so it has length delta S. Okay, that's a piece of C. And the other side is going to be given by my velocity vector F. And to find the height of this thing, I need to know, well, what is actually the normal component of this vector. Right? So if I call n the unit normal vector to the curve, then the area is base times height is just, so the base is delta S, and the height is the normal component of F, so it's F dot n. And so you see that when you sum these things together, you get what I said. You get flux. Now, if you're worried about the fact that actually, if your unit time is too long, then of course things might start changing, as the fluid flows. I mean, it might. So you have to take a time unit and a length unit that are sufficiently small so that really this approximation, where C is a straight line and the flow is at constant speed, are valid. So, you want to take maybe a segment here that's like a few micrometers, and, the time unit might be a few nanoseconds or whatever, and then it's a good approximation. So what I mean by per unit time, actually, it's the, well, yeah, actually, that works, but you want to think of a really, really small time, and then the amount of matter that passes in that really, really small time is the flux times the amount of time. Okay, let's be a tiny bit more careful. When I'm saying it's the amount of stuff that passes through C, well, it depends actually on whether n is going this way or the opposite way. So actually, what's implicit in this explanation is that I'm counting positively all the stuff that flows across C in the direction of n, and negatively what flows in the opposite direction. Okay, so what flows to the right of C, towards, well, across C, from left to right, is counted positively, while what flows right to left is counted negatively. Okay, so in fact, it's the net flow through C per unit time. Okay, any questions about the definition or the interpretation or things like that? Yes? How do you, sorry?
How do you have both, positive and negative, or in one segment?
Well, you can have both, not in the same small segment, but it could be that, well, imagine that my vector field, here suddenly goes in the opposite direction. Then this part of the curve, well, things are flowing to the left, so this part of the curve contributes negatively to flux. And here, maybe the field is tangent, so the normal component becomes 0, and then it becomes positive, and this part of the curve contributes positively. For example, if you imagine that you have a round tank in which the fluid is rotating, and you put your dam, just on a diameter across, then things are going one way on one side, the other way on the other side, and actually it just evens out. So we don't have complete information. It's just the total net flux. Okay. So if there's no other questions, then I guess we'll need to figure out how to compute this guy and how to actually do this line integral. So, well, let's start with a couple of easy examples. Okay, so let's say that C is a circle of radius A centered at the origin, going counterclockwise. And let's say that our vector field is xi plus yj. So what does that look like? So remember, xi plus yj is a vector field that's pointing radially away from the origin. Right? Because at every point, it's equal to the vector from the origin to that point. So now, if we have a circle, and let's say we're going counterclockwise. So actually, I have a nicer picture, so let me do it here. Okay, so that's my curve and my vector field. And, well, so the normal vector, see, when you go counterclockwise on a closed curve, this convention that the normal vector points to the right of a curve makes it point out. So the usual convention when you take flux through a closed curve is that you're counting the flux going out of the region enclosed by the curve. I mean, of course, if you went clockwise, it would be the other way around. You choose to do it the way you want, but the most common one is to count flux going out of a region. So let's see what happens. Well, if I'm anywhere on my circle, see, the normal vector is sticking straight out of a circle. Right? That's a property of a circle, that the radial direction is perpendicular to the circle. So actually, let me complete a bit this picture. If I take a point on the circle, I have my normal vector that's pointing straight out. So it's parallel to F. Okay, so along C, we know that F is parallel to N. So F dot N will be equal to the length, the magnitude of F, times, well, the magnitude of N, but that's 1. Okay, let me put it anyway, but that's a unit normal vector. Now, what's the magnitude of this vector field if I'm at a point x, y? Well, it's square root of x squared plus y squared. That's the same as the distance from the origin. Okay, so if this distance, if this radius is a, then the magnitude of f will just be a. Right? So, in fact, f dot n is constant, always equal to a, so the line integral will be pretty easy, because all I have to do is the integral of f dot n ds, becomes the integral of a ds. A is a constant, so I can take it out. And integral ds is just the length of C, which is 2 pi a. So I will get 2 pi a squared. Okay? And that is positive, as we expected, because stuff is flowing out of a circle. Okay, any questions about that? No? Okay. Just out of curiosity, let's say that we had taken our other favorite vector field. So let's say that we had the same C, but now the vector field negative y comma x. So remember that one goes counterclockwise around the origin. Okay? So if you remember what we did several times, well, along the circle, that vector field now is tangent to the circle. So if it's tangent to the circle, it doesn't have any normal component. The normal component is 0. Right? Things are not flowing into the circle or out of it. They're just flowing along the circle, around and around. So the flux will be 0. Okay, F now is tangent to C. So F dot n is 0, and therefore the flux will be 0. Okay, so these are examples where you can compute things geometrically. And I would say, generally speaking, with flux, you know, well, if it's a very complicated field, then you can't. But if a field is fairly simple, you should be able to get some general feeling for whether your answer at least should be positive, negative, or 0, just by thinking about which way is my flow going. Is it going across the curve one way or the other way? Okay. Still no questions about these examples? No? Okay, so next thing we need to know is how we'll actually compute these things. You know, because, yeah, here it works pretty well, but what if you don't have a simple geometric interpretation? What if I give you a really complicated curve, and you know, then you have trouble finding the normal vector? It's going to be annoying to set up things this way. So actually, there's a better way to do it in coordinates. Just as, you know, when we do work, when we compute this line integral, usually we don't do it geometrically like this. Most of the time, we just integrate m dx plus n dy in coordinates. So there's a similar way to do it because it's again a line integral, so it should work the same way. So let's try to figure that out. Okay, so how do we do the calculation in coordinates? Or I should say maybe using components. So, you know, that's the general method of calculation when we don't have something geometric to do. So remember, when we were doing things for work, we said this vector dr, or if you prefer t ds, we said just becomes symbolically dx and dy. So that, you know, when you do the line integral of f dot dr, you get line integral of m dx plus n dy. So now let's think for a second about how we would express NDS. Well, what is NDS compared to TDS? Well, N is just T rotated by 90 degrees, so NDS is TDS rotated by 90 degrees. That might sound a little bit outrageous because these are really symbolic notations, but it works. So probably I'm not going to spend too much time trying to convince you carefully, but really, if you go back to where we wrote this and how we try to justify this, and you work your way through it, you will see that NDS can be analyzed the same way. So N is T rotated 90 degrees clockwise. So that tells us that NDS is, so how do we rotate a vector by 90 degrees? Well, we swap the two components and we put a minus sign. So swap them, you have dy and dx, and you have to be careful where to put the minus sign. Well, if you're doing it clockwise, it's in front of dx. Well, actually, let me just convince you quickly by, let's say we have a small piece of C. So if we do T delta S, okay, T delta S, that's also vector dr, if you put delta r, sorry. That's going to be just, the vector that goes along the curve. It's given by this. So its components will be indeed the change in x, delta x, and the change in y, delta y. And now if I want to get n delta s, well, I claim now it's perfectly valid and rigorous to just rotate that by 90 degrees. So I lost my red chalk. Here it is. So if I want to rotate this by 90 degrees clockwise, then the x component will become the same as the old y component. And the y component will be minus delta x. And then you take the limit when the segment becomes shorter and shorter, and that's how you can justify this. Okay? So that's the key to computing things in practice. It means actually you already know how to compute line integrals for flux. Let me just write it explicitly. So let's say that our vector field has two components. So let me just confuse you a little bit and not call them m and n for this time, just to stress out, just to stress the fact that we are doing a different line integral. So let me call them p and q for now. Then the line integral of f dot n ds will be the line integral of, well, pq dot product, where is it? dy negative dx. So that will be the integral of negative q dx plus p d. Well, I'm running out of space here. It's integral along C of negative q dx plus p dy. Okay, and from that point onwards, you just do it the usual way. Namely, you remember, here you have two variables, x and y, but you're integrating along a curve. So if you're integrating along a curve, x and y are related. They depend on each other or maybe on some other parameter like t or theta or whatever. So you express everything in terms of a single variable, and then you do a usual single integral. Okay, any questions about that? I see a lot of confused faces. So maybe I shouldn't have called my components P and Q. So Okay. So if you prefer, okay, so if you're really sentimentally attached to m and n, then this new line integral becomes the integral of minus n dx plus m dy. Okay? So, if a problem tells you compute flux instead of saying compute work, the only thing you change is instead of doing m dx plus n dy, you do minus n dx plus m dy. And I'm sorry to say I don't have any good way of helping you remember which one of the two gets the minus sign. So, you just have to remember this formula by heart. That's the only way I know. Well, I mean, you can try to, go through this argument again, but it's really best if you just remember that formula. Okay. So I'm not going to do an example because we already know how to do line integrals. Okay? But hopefully you will get to see one at least in recitation on Monday. Okay, so that's all pretty good. Let me tell you now, what if I have to compute flux along a closed curve and I don't want to compute it? So, well, remember, in the case of work, we had Green's theorem. We saw yesterday Green's theorem lets us replace a line integral along a closed curve by a double integral. Well, here it's the same. We have a line integral along a curve. We should be able, if it's a closed curve, we should be able to replace it by a double integral. So there is a version of Green's theorem for flux. And you'll see it's not more scary than the other one. It's perhaps less scary or perhaps just as scary or just as not scary, depending on how you feel about it. But it works pretty much the same way. Okay, so what does Green's theorem for flux say? So it says if C is a curve that encloses a region R counterclockwise, and if I have a vector field that's defined everywhere, not just on C, but also inside, so also on R, defined, well, and differentiable and so on, in R, well, maybe I should give names to the components. So if you'll forgive me for a second, I will still use P and Q for now. You'll see why. Is defined and differentiable in R, then I can actually replace the line integral for flux by a double integral over R of some function. And that function is called the divergence of f dA. Okay, so this is the divergence of f. And I have to define for you what this guy is. So the divergence of a vector field with components P and Q is just P sub x plus Q sub y. So this one is actually easier to remember than curl, right? Because you just take the x component, take its partial with respect to x. Take the y component, take its partial with respect to y, and add them together. No signs, no switching things around. This one is pretty straightforward. Okay, so the picture, again, is if I have my curve C going counterclockwise around the region R, and I want to find the flux of some vector field F that is everywhere in here. So maybe some parts of C will contribute positively, some parts will contribute negatively. Anyway, just to reiterate what I said, positively here means, because we are going counterclockwise, the normal vector points out of the region. Okay, so this guy here is the flux out of R through C. Okay. So that's the formula. Any questions about what the statement says or how to use it concretely? No? Okay, so it's pretty similar to Green's theorem for work. So actually I should say, sorry, maybe I should say, this is called Green's theorem in normal form also. So not that the other one is abnormal, but just that, you know, the old one for work was, you could say, in tangential form. That just means, well, Green's theorem, as seen yesterday, was for the line integral f dot t ds, integrating the tangent component of f, sorry. The one today is for integrating the normal component of f. Okay, let's prove this. So, good news, it's much easier to prove than the one we did yesterday because we're just going to show that it's the same thing, just using different notations. So how do I prove it? Well, maybe actually it would help if first, before proving it, I actually rewrite what it means in components. Okay. So we said the line integral of f dot n ds is actually the line integral of negative q dx plus p dy. Right? And we want to show that this is equal to the double integral of p sub x plus q sub y dA. So this looks a lot like, you know, this is really one of the features of Green's theorem. No matter which form it's in, it relates a line integral to a double integral. So let's just try to see if we can reduce it to the one we had yesterday. So, you know, let me forget what these things mean physically and just focus on the math. On the math, it's a line integral of something dx plus something dy. So let's call this guy m, and let's call this guy n. Okay? So let m equals negative q, and n equals p. Then I know, well, this guy here becomes integral of m dx plus n dy, and I know from yesterday what this is equal to, namely using the tangential form of Green's theorem. Green for work, this is the double integral of curl of this guy. So that's nx minus my dA. But now let's think about what this is in terms of m and n. Well, we said that m is negative q, so this is negative my. And we said p is the same as n, so this is nx. So see, just by renaming the components, I go from one form to the other one. So it's really the same theorem. That's why it's also called Green's theorem. But the way we think about it when we use it is different, because one of them computes the work done by a force along a closed curve. The other one computes the flux, maybe of a velocity field, out of a closed region, out of a region. Okay, questions? Yes?
So when we compute one, we can just rename them and compute the other one as we know how to?
Yeah, that's correct. So if you're trying to compute, a line integral for flux, you see it just becomes, wait, where did I put it? So the line integral for flux just becomes this, and once you're here, you know how to compute that kind of thing. The double integral side, there's not even any kind of renaming to do. You know how to compute a double integral of a function, and this is just a particular kind of function that you get out of a vector field. But it's any function, it's like any function. The way you would evaluate these double integrals is just the usual way. Namely, you have a function of x and y, you have a region, and you set up the bounds for the iterated integral. Quiet, please. There's a lot of people talking, but okay. So the way you would evaluate the double integrals is really the usual way, by slicing the region and setting up the bounds for iterated integrals in dx dy or dy dx, or maybe rd d theta or whatever you want. So in fact, in terms of computing integrals, we just have two sets of skills. One is setting up evaluating double integrals. The other one is setting up evaluating line integrals. And whether these line integrals or double integrals are representing a work, a flux, integral of a curl, whatever, the way that we actually compute them is the same. Okay? Okay, let's do an example. Oh, by the way, no, so first, sorry. So this renaming here, see, that's why actually I called my components P and Q, because the argument would have gotten very messy if I had told you, oh, well, now I call M n and I call n minus m and so on. But now that we're done, now that we're through with this, if you still like m and n better, then what this says then the formulation of Green's theorem in this language is just integral of minus n dx plus m dy is double integral over R of mx plus ny dA. Okay. Okay, so now let's do an example. Let's look at this picture again, the flux of xi plus yj out of a circle of radius a. So we did the calculation directly using geometry, and it wasn't all that bad. But let's see what Green's theorem does for us here. Okay, so example. Let's take the same example as last time. So xi plus yj through C, the circle of radius a, counterclockwise. Okay, so how do we set up Green's theorem? Well, let's first figure out the divergence of f. Bless you. So the divergence of this field, I take the x component, which is x, and I take its partial respect to x. And then I do the same with the y component, and I will get 1 plus 1 equals 2. Okay, so the divergence of this field is 2. Now, Green's theorem tells us that the flux out of this region is going to be the double integral of 2 dA. Where what is R now? Well, R is the region enclosed by C. So if C is this circle, R is the disk of radius A. So of course we can compute it, but we don't have to, because double integral of 2 dA is just twice the double integral of dA, so it's twice the area of R, and we know the area of a circle of radius A, that's pi a squared. So that's 2 pi a squared. Okay, that's the same answer that we got directly, which is good news. So now we can even do better. Let's say that my circle is not at the origin. Let's say that it's out here. Well, then it becomes harder to calculate the flux directly. And it's harder even to guess exactly what will happen because on this side here, well, the vector field will go into the region. So the contribution to flux will be negative here. Well, here it will be positive because it's going out of the region. So there's positive, there's negative terms. Well, it looks like positive should win because here the vector field is much larger than over there. But, computing, short of computing it, we won't actually know what it is. So if you want to do it by direct calculation, then you have to parameterize this circle and figure out, what the line integral will be. But if you use Green's theorem, well, we never used the fact that it's the circle of radius a at the origin. Right? It's true actually for any closed curve that the flux out of it is going to be twice the area of the region inside. So it will still be 2 pi a squared even if my circle is anywhere else in the plane. So, if I had asked you the trick question, where do you want to place this circle so that the flux is the largest? Well, the answer is actually it doesn't matter. Okay. Now, let's just finish quickly by answering a question that some of you, I'm sure, must have, which is, what does divergence mean? What does it measure? Right? I mean, we say it for curl. Curl measures how much things are rotating somehow. So what does the divergence mean? Well, the answer is divergence measures how much things are diverging. Okay, that's let's be more explicit. So interpretation of divergence actually, you can think of it, imagine that, so what do I want to say first? So if you take a vector field that just like maybe, that's a constant vector field where everything just translates, then there's no divergence involved because the derivatives will be 0. If you take the guy that rotates things around, you'll also compute and find 0 for divergence. So this is not sensitive to translation motions where everything moves together or to rotation motions. But instead, it's sensitive to expanding motions. So a possible answer is that it measures how much the flow is expanding areas. Okay, so if you imagine this flow that we have here on that picture, things are moving away from the origin and they fill out the plane. If you imagine this fluid flowing out there, it's occupying more and more space. And so that's what it means to have positive divergence. If you took the opposite vector field that contracts everything to the origin, that would have negative divergence. So that's a good way to think about it if you're thinking of a gas, maybe, that can expand to fill out more volume. If you're thinking of water, well, water doesn't really shrink or expand. So the fact that it's taking more and more space actually means that there's more and more water. So the other way to think about it is divergence is the source rate. So it's the amount of fluid that's being inserted into the system, that's being pumped into the system per unit time, per unit area. Per unit time and per unit area. So what div f equals 2 here means is that here you have actually matter being created or being pumped into the system so that you have more and more water filling more and more space as it flows. But actually, divergence is not 2 just at the origin, it's 2 everywhere. So in fact, to have this, you need to have a system of pumps that actually is inserting water absolutely everywhere uniformly. That's the only way to do this. I mean, if you imagine that you just have one spring at the origin, then sure, water will flow out But as you go further and further away, it will do so more and more slowly. While here, it's flowing away faster and faster. And that means, everywhere, actually, you're still pumping more water into it. So that's what divergence measures.